and welcome to this lecture. This lecture is about one of the most celebrated results of probability theory. It's called the central limit theorem. Okay, you might have heard this somewhere, the bell-shaped curve and where it comes from and how the bell is everywhere. Everywhere you look at, you have this bell-shaped curve in the distribution, etc., etc. The central limit theorem is behind all of that. It's a very classic, celebrated result, and it's important in any probability course to understand it cleanly. And you will see this moment generating function that it describes sort of plays a central role. It ties up this very well. There is a little bit more of analytical wizardry involved there. We won't spend too much time on that, but I'll at least point out where this comes from. Okay, so it's a very powerful result. You will see finally when we want to look at the binomial distribution, right? We were looking at this probabilities of y deviating from its expected value, the binomial random variable deviating from its expected value. We had the Chebyshev bound, we saw the Chernoff bound. None of them were really close to the actual probability. You will see the central limit theorem will give you a very good approximation to the binomial particularly. Okay, so it's a very useful, powerful result. I'll make more remarks on what it means, etc. But let's jump into it. Okay. Okay, so let me define this moment generating function. I did refer to it before, we have seen it before, but I want to talk a little bit more about it and get started and in a slightly more formal fashion with the moment generating function. Okay, so let's start with the zero mean random variable. Once again, this is not a big issue. So supposing you have a random variable which is not zero mean, what do? You simply subtract the expected value, you get a zero mean. So you go to that, and then you know that translating doesn't change anything. Any event with the original one is simply translate. So it's all easy to go back and forth with this. Okay, so the MGF of x, it's denoted mx of lambda. I'll use this notation, mx of lambda. It's a function from the real numbers to real numbers. It says r to r here, so you can put a math bb here. I should change that. So it's from r to r, and it's defined as mx of lambda is expected value of e power lambda x. Now convince yourself that this is a function from the real numbers to real numbers. Okay, lambda is a real number, right? Given a real number lambda, particular value for lambda, 1, 2, 1.5, 3.5, pi squared, e squared, whatever the value of lambda is, it's a real number. I can just do expected value of e power lambda x. X is some distribution, but expected value of e power lambda x is going to give me a number. Okay, so this is a mapping from real numbers to real numbers. It's a function. Okay, so it has that nice looking form, expected value of e power lambda x. Okay, so now supposing x is discrete, it has a PMF fx, and you know the PMF. Okay, so usually we assume that. So basically x will take values small x1, small x2, so on. What is the probability it takes value small x1? Fx of x1. What's the probability it takes value x2? Fx of x2. So what is mx of lambda? It's expected value of e power lambda x. So it's e power lambda x1 times the probability that x takes value x1, which is fx of x1, plus e power lambda x2 times the probability that it takes the value x2, and so on. Okay. Very simple, isn't it? I mean, it looks a bit more complicated notation. When you actually break it down and look at what's going on, it's a very, very simple calculation. Now it turns out it can also be used for continuous distributions. Okay, so we have seen these continuous distributions before. When you have a density fx and some support tx, you can again define mx of lambda. It's just the expectation. Now except that the expectation is not summation anymore. You remember from discrete to continuous, when you go, the expectation becomes integration. You have to integrate over the range e power lambda x fx of lambda dx. Okay, over x you integrate. I made a mistake here. This is a huge mistake. Apologies for that. It's fx of x. Okay, it's not fx of lambda. Okay, sorry. So it's the density times e power lambda x dx. Okay, so if you want a picture, for this continuous thing, supposing this is your fx of x, you will have a e power lambda x, right? So e power lambda x, let's say lambda is positive. Okay, so e power lambda x. So you will multiply these two. So you multiply these two and integrate. Multiply and integrate. That's all. Okay, numerically there's nothing in this problem, right? So you have e power lambda x. For different lambda, you'll get different e power lambda x. Of course, if lambda is negative, it will go the other way, right? It will go this way. But it doesn't matter, fx of x stays the same. You just multiply these two functions and integrate. Okay. So it's very simple definition in some sense. If you have a numerical tool, you can do it. If you know enough integration, you can also get closed form expressions for these integrals and all that. We won't spend too much time on this, but I want you to know that the MGF is a simple calculation involving the exponential function, of course, but it's just an expectation calculation. Okay, so nothing to be very alarmed about. Let's see examples. Okay, examples are always very nice. So we'll start with the simplest possible example. Okay, in this case, it's a ridiculous distribution. I'm going to say x equals 0. I'm taking a random variable which takes only one value with probability 1. Okay, so if you look at mx of lambda, it just becomes 1, right? So it's 1 into e power 0. Well, lambda times 0 is again 0. It's just 1. Okay, so easy enough. Seems very simple. You can also take other constants. If x is not 0, then of course expected value of x is not 0, right? So you have to pull it down to this, and you can try that. So that's why 0 is meaningful. Okay, so let's take this next distribution, which is sort of like Bernoulli P. Okay, so this is actually what? Centralized Bernoulli P. Do you agree? Centralized Bernoulli P, right? So what is Bernoulli P? Bernoulli is 0, 1, P 1 minus P, okay? Expected value equals P, okay? Now I'm going to subtract P from this, minus P, and you get minus P, 1 minus P, probability remains the same. That becomes centralized Bernoulli. Okay, so expected value is 0. Okay, so it's just a simple centralization. So you get minus p with probability 1 minus p and 1 minus p with probability p. So for p equals half is what we saw before, right? Minus half, half with probability half, half each. Okay, so if you do the moment generating function for this, you will again get 1 minus p times e power minus p lambda plus p times e power 1 minus p lambda. Okay, you can put p equals half. We will recover the previous result that we had for centralized Bernoulli half. Okay, so here is a slightly different random variable. Okay, so this is again a discrete random variable. It takes 3 different values: minus 1 with probability half, 0 with probability 1 by 4, and 2 with probability 1 by 4. You can check its expected value is 0. I've centralized it, sort of make sure that it works. Now, if you write down mx of lambda, it's going to be half times e power minus lambda plus 0.25 times e power lambda into 0, that becomes just 1, plus 0.25 times e power 2 lambda. Okay, I want to point out one thing. Just pause for a second. If I give you the distribution, you are able to go to the mx of lambda. If I give you an mx of lambda in this form, you can go back to the distribution, right? Think about this. Okay, right? So particularly with this e power lambda, e power minus lambda form, if I give you the distribution, you go to the mx of lambda. If I don't give you the distribution, if I give you the mx of lambda, you can also go back to the distribution. Okay, so it's very easy. So let me show you how that is done here. So here I've given you an mx of lambda, which is 1 by 3 e power 3 lambda by 2 plus 1 by 6 e power minus 3 lambda plus 1 by 8 e power minus lambda plus 1 by 8 e power lambda plus 1 by 8. Okay, this is the mx of lambda I have given to you. From here, you can almost read out 1 by 1 what value it takes. Notice this expression here, 1 by 6 e power minus 3 lambda actually gives you the distribution directly. You can just read off from every term here, you can read off one particular value that x takes. Okay, so notice this term here. Okay, 1 by 3 e power 3 lambda by 2. It means that x takes value 3 by 2. Okay, so this gives you x takes value 3 by 2 with probability 1 by 3, right? So this directly gives you this value, right? Remember this expected value of e power lambda x. So x takes value 3 by 2 with probability 1 by 3. Okay, you can go back to the formula. It is just the direct formula, right? So expected value of e power lambda x will be plus xi, plus fx of xi times e power lambda xi, isn't it? So it will have a term like this, x takes, so this implies x takes value xi with probability fx of xi. right? So you can go from the distribution to the particular term of fmx of lambda, or you can take the particular term of mx of lambda and go to the distribution. That's what I'm doing here in reverse, okay? So this is an important idea, okay? The distribution fixes the moment generating function. The moment generating function also fixes the distribution. So from going from distribution to moment generating function is one-to-one, okay? So notice this one-to-one relationship. To describe a random variable x, you can either give the actual distribution or you can give its moment generating function. Both are one and the same, so they go back and forth, okay? It's an important thing to remember, okay? So you see here 3 by 2 with probability half. What about this guy, this term here? So maybe I'll use a different color, okay? So you see this term here, this gives you this guy, right? X takes value minus 3 with probability 1 by 6. So likewise you can see every term, x takes value minus 1 with probability 1 by 8, x takes value 0 with probability 1 by 8. Did I get this right? I think this is wrong. Okay, now I know what mistake I made. This is not a valid distribution, so it turns out this needs to be 1 by 4. Thought I corrected it, okay. So this will have to be 1 by 4 for this to be a valid distribution. Apologies for that. Okay, so this is correct. So you have minus 1 with probability 1 by 8 and 1 with probability 1 by 8 and 0 with probability 1 by 4. Notice this value is important to understand. So this gives you x taking value 0 with probability 1 by 4. Okay, so it's like e power lambda into 0. Okay, so you have to think of the 1 as being, you know, e power lambda into 0. So notice how the MGF directly gives you the distribution also. You can go from distribution to MGF or MGF to distribution. It's a one-to-one relationship. It's a useful thing, useful skill to build up and understand what's going on. And finally, if x is normal 0 sigma square, this is a very, very, very important result, extremely important. I've just put it as the last example. Let me put 5 stars next to it and 5 stars to the left of it to drive home the point that if there is one MGF that you have to mug up by heart and remember, it's the MGF of the normal distribution. Normal distribution with mean 0 and variance sigma squared, the MGF is e power lambda square sigma squared by 2. Okay, just mug it up by heart. If somebody wakes you up in the middle of the night and asks you, you should be able to say, okay, MGF of normal 0 mean variance sigma square is e power lambda square sigma squared by 2. Okay, very, very important to know this. So how do you prove this? I mean, it's not, so I'll leave it as an exercise. So it's basically minus infinity to infinity e power lambda x, right? And then you have this 1 by root 2 pi sigma e power minus x squared by 2 sigma squared dx. This guy you can show is actually equal to this. Okay, so this is an exercise in integration. It involves, you know, completing the square and the numerator and in the exponent and all that. And I don't want to go into the details here. This is an exercise for you. Look it up. If one of you, you know, can solve this, please post on the discourse forum a solution to how this came about, and everybody would appreciate that. Okay, so this is an exercise for you to do and post on the discourse forum. Okay, so this is examples. Hopefully this conveys to you how to work with MGFs. Generally discrete you see is very easy, but continuous is a little bit more involved, involves integration. I'm not going to expect that you know all these integration steps, but if you know, do share and let people also come out. What's important is the final result. The final result is really, really important. You should know that by heart. Okay, so why moment generating function? Where is that moment and generating and all that is coming from? Here's the reason for that. Okay, so you can expand e power lambda x as 1 plus lambda x plus lambda squared by 2 factorial x squared, etc., etc. Okay, both of these should give you the same function. I mean, I know I formally didn't define any random variable exponentiation and all that. We are not going to do all that. Just intuitively you can see why this has to be true, and that's good enough for us. Okay, so you see this is just the exponential e power x expansion. E power x is 1 plus x squared by 2 factorial x cubed by 3 factorial, so on. So that's the expansion I've done here. Okay, now expected value distributes inside summation, assuming convergences, etc., etc. All of that is going on. So expectation will go in, and expected value of 1 is just 1 plus lambda times expected value of x plus lambda squared by 2 factorial expected value of x squared, expected value of x cubed, so on, so on, so on. So expected value of e power lambda x, if you were to write it as an expression in terms of lambda, lambda squared, lambda cube and all that, the coefficients give you the moments. So these are called moments. This is the first moment or the mean. This is the, let me write it out properly, first moment. This is the second moment, so on. Okay. This is the third moment, and this is the MGF. So MGF is basically an expansion. If you expand the MGF as a polynomial series in lambda, then you get the first moment, second moment, third moment, and all that. Okay. So here's an example. Okay. So let's take this example. It's normal distribution, 0 mean variance sigma squared. The moment generating function is e power lambda square sigma squared by 2. Okay. So you expand on the left side, you get this expression. You expand on the right side, e power x is 1 plus x squared by 2 factorial. I am writing the x squared by 2 factorial in a different way here. This term is actually equal to lambda squared sigma squared by 2 whole squared by 2 factorial. It's the same as that. Okay. So I put a 3 there, this 2 squared will become 4. 3 in the numerator, 3 in the denominator will make it 4 factorial lambda power 4. Why am I doing lambda power 4 by 4 factorial? Only then it will look like the left hand side, right? So it will look exactly like the left hand side, and that's what I want. So once I have an expression like this, I can read off moments. Expected value of x is 0, expected value of x squared is sigma squared, right? It's just the coefficients, lambda squared by 2 factorial, the coefficient is expected value of x squared on the left hand side, sigma squared on the right hand side. Anytime you have equality like this, which is true for every lambda, okay, then you can read off the corresponding things. I mean, of course, convergence, so many things are involved here, but we'll assume all that. Okay, expected value of x cube is 0. Expected value of x power 4 is 3 times sigma power 4. Okay, a result that is not so difficult. It's a little bit more difficult to derive if you were just doing integration. Okay, so from the MGF you can do this, and you can just keep going on and on and on and on and on. Okay. So this is why it's called the moment generating function. This is not so important to us in this class, but this is the reason why it's called that. Okay. Okay. Now what's more important to us is the connection between MGF and sums of independent random variables. We already saw this before, right? When we did the Chernoff bound for the binomial case, this was very, very useful. Now let's generalize. Let's see how to do this. Okay. So let's say we have two random variables which are IID according to some distribution, and I'm defining the sum of those two random variables, y equals x1 plus x2, that's it. Okay. So let me start with one simple example, x being IID Bernoulli P. Okay. So here the moment generating function will work out as what I've shown there, 1 minus p times e power minus p lambda plus p times, so this is just the usual, I mean this is actually the centralized Bernoulli, isn't it? So this is, okay, so I should be careful here, so I should write centralized. Okay, so we're all doing centralized, so this is just minus p, 1 minus p with probability p and with probability 1 minus p, right? So that's the expression that we got here. And now my of lambda, okay, because this is IID, is going to be mx of lambda whole squared. Okay, so I can just take this guy and square it. Okay, so this is just the square of, so this is squared. So when you square, you get this expression, right? It's a squared plus b squared plus 2ab. That's what you get. And from here, you can read out the distribution. Okay. So I went from distribution to mx of lambda, and then I squared mx of lambda to get my of lambda, and from my of lambda, I can read out the distribution. Okay, so it's 1 minus p whole squared times e power minus 2p lambda. So it takes value of minus 2p with probability 1 minus p whole squared. Takes value 1 minus 2p with probability 2p into 1 minus p, and takes value 2 times 1 minus p with probability p squared. Okay, so this is a way to find the distribution of the sum of two random variables which are independent by using the moment generating function. Okay, so this is very important to understand. So we know that there is a tie-in between the MGF and the sum, but this is, I'm just showing you examples of how you can use MGF to actually find the distribution of the sum of two independent random variables, and it's very, very simple and direct. Okay, so here's another example. Okay, slightly more twisted example. It's not centralized Bernoulli anymore. Minus 1, 0, 2. You have this other complicated looking distribution. Mx of lambda is this. You just square it. You get my of lambda. From there you can read out the distribution. I'm not writing down the distribution, but from the my of lambda you can see it takes value minus 2 with probability 1 by 4, minus 1 with probability 1 by 4, 0 with probability 0.0625, 1 with probability 0.25, etc. So you can read out the value. So here is yet another distribution, which is a little bit more complicated. You remember I had this distribution before, 1 by 3 power 3 lambda by 2 plus 1 by 6 and all that. And then if you square it, you will get this my of lambda. So look at this ugly little expression here, but nevertheless you can read out every value. It takes value minus 6 with probability 1 by 36. It takes value minus 3 by 2 with probability 1 by 9. It takes value 0 with probability 3 by 32. So from the moment generating function, you can read out the probabilities very, very easily. Okay, seems simple enough for small cases, but its real power comes when you use it for large n. Okay, how do we use it? Let me show you. Let's look at the MGF of the sample mean. Okay, now my samples x1 through xn are IIDx, and my x is centralized Bernoulli half. Okay, so that's why my moment generating function became e power lambda by 2 plus e power minus lambda by 2. So x is centralized Bernoulli half. Okay, so that's the distribution for the x. Okay, now what is my sample mean? It's going to be x bar, which is x1 plus dot plus xn divided by n. Okay, so far we never saw the divided by n. Okay, so far we just looked at x1 plus xn. We never concerned ourselves with this division by n. Now this division by n is very, very critical. Now what I'm going to do is I'm going to write this as simply x1 by n plus x2 by n plus dot xn by n. Okay, now what is this? This is, what is x by n? Okay, what is x by n? Now this x is centralized Bernoulli, so x is minus half with probability half. Okay, x by n is actually minus 1 by 2n and 1 by 2n with probability half. It gets shrunk, right? So if you think of x as being minus half with probability half, as n increases, this comes down and down. So it becomes minus 1 by 2n, 1 by 2n. The probability half remains the same. Probability equals half. This is probability. That remains the same at half, but as you increase n, it keeps coming down and down and down. So each of these guys, right? So if you look at the sequence, x1 by n, x2 by n, so on till xn by n, these are IID according to x by n. Okay, so that's the story here. Okay, now all I need to do is find the moment generating function for x by n. Okay, and then from there I can go to the moment generating function of x bar, simply raising it to the power n. Okay, that's what has happened here. Okay, so the moment generating function for x by n is e power 1 by n lambda plus e power minus lambda by 2n divided by 2. Okay, so it's half into, so this is basically half into e power lambda into minus 1 by 2n plus half into e power lambda into 1 by 2. It takes value 1 by 2n with probability half, minus 1 by 2n with probability half. This is just just addition and writing it up. So once you find mx by n, what is the moment generating function for x bar? It is just the IID sum of x by n distribution. So it is just this moment generating function raised to the power n, e power lambda by 2n plus e power minus lambda by 2n by 2 raised to the power n. Remember, this is just a function of lambda. Okay, so there is just one variable here. N is just like a parameter, so it is just a function of lambda. Okay, keep that in mind. Okay, so we are able to find the MGF of sample mean for the case of centralized Bernoulli quite easily, and we write it down. You get an expression like that. So now what you can do is you can plot. Okay, so here is a plot for the MGF of the sample mean mx bar of lambda was as a function of lambda for different n. Okay, so you can see what is going on here. It's really, really interesting. I'm starting with n equals 1. I get a big cup like this. So notice the y-axis here. It's around 1. Okay, 0.9997 to 1.0004. It's very close to 1. I've just zoomed up the area around 1. Okay, that's what I've done here. And then I plot for n equals 10. Notice what's going on here. It's just sort of shrunk down. And then for n equals 20, 50, 100. And notice what's going on. As you keep increasing n, we observe, at least visually, Okay, even though we have not proved this analytically, we won't prove it. You can prove it if you like to, but it's if it keeps coming down, coming down, it becomes flat. And it's a fact that this mx bar of lambda will tend to 1 as n increases, as n goes to infinity. Okay, so this should not be surprising to you. Why should this not be surprising to you? Because we already know from the weak law of large numbers there is some sort of a conversion for x bar, a convergence for x bar towards the expected value. What is the expected value of x? It's centralized Bernoulli half, of course, is 0. So I know x bar is somehow converging to 0. And what is the MGF of the constant 0? It should be the flat function 1. Okay, so this MGF is actually converging to the flat function 1, which is the expected value of x. Okay, so it's not very surprising, but look at this very nice picture that you can draw with this. Okay, what I'm going to do next is one very subtle and very profound change to what I've done here. Okay, so the one thing that is crucial is this division by n. Okay, and I got this division by n and then raised it to the power n, and I got this wonderful convergence to something flat. What if I change n? Okay, so this is a very profound and subtle question. What if I change n? Instead of dividing by n, what if I divide by something else? What is that something else? Why is that crucial? All that is a little bit deep and a little bit involved. Maybe I'll point you to something interesting later on that. But let's try it. Let's see what happens in the same case. If we divide, instead of n, we divide with root n. Okay, so you can ask me, where is the root n coming from? Why is it well motivated and all that? Maybe I'll give you some pointers to why the root n becomes important here. But it's crucial. This root n scaling instead of 1 by n scaling changes things fundamentally and in a very, very interesting way. Okay, so the setting is same as before. I have IID samples according to centralized Bernoulli. Expected value of x is 0, variance of x is 1 by 4. Note that down. The variance will not change when you translate, right? It's just 1 by 4. Now, previously I considered x1 plus xn divided by n. That was the sample mean. Now, I'm going to consider this other scaling, which is division by root n instead of n. Once again, you may ask, why root n? What is so special about it? You will see the result is really special when root n comes in. Okay, you'll see why that's really, really special, but it's a bit profound and very interesting that root n causes this kind of a fundamental change in what happens to the MGF. Now, I mean, technically the derivation, there's nothing different. Whether I divide by n or root n, it's the same thing, right? Instead of x, I will look at the moment generating function for x by root n. So instead of 1 by 2n, minus 1 by 2n, I'll have 1 by 2 root n minus 1 by 2 root n. Nothing changes there. And so the moment generating function for y is simply this e power lambda by 2 root n plus e power minus lambda by 2 root n by 2 raised to the power n. So all these mechanics, there's no change, and you can use Desmos or something. You can easily generate this and plot. Okay, so that's what I've done here. Notice the profound change. Okay, look at the huge change here. Okay, so I'll walk you through how I've plotted it. This my I've plotted for different values of n. First is n equals 1. Okay, so you see for n equals 1, it will just be the e power lambda by 2 plus e power minus lambda by 2. I told you how it looks. No, it looks like e power lambda squared. Okay, it will look like this. This e power lambda square will look like this u, right? So it's sort of like this e power lambda square. Okay, notice what happens as you keep increasing. So I put a t here. I apologize for that. It should be lambda e power minus lambda squared by 4 by 8. Okay, it's not minus also. Okay, so this is wrong. So let me just this should just be lambda e power lambda squared by 4 8. Okay. So I have the blue line for n equals 1, that is sort of like that. And then notice what happens when n becomes equal to 10, and then when n becomes equal to 20, it is not converging to something flat, it's converging to something that looks like e power lambda squared, some e power lambda squared by 8 or something. In fact, you can see that e power lambda squared by 8 is exact, and if you do a little bit of work here, you can show that this will converge to e power lambda square sigma squared by 2 as n increases. And what is sigma squared? This guy is sigma squared. Okay, sigma squared is 1 by 4. Okay, so you see e power lambda squared by 8. That's what this converges to, e power lambda squared by 8. Okay, so this is nothing short of magic, it turns out. So you may say it's one special case for if you put n, you're getting a flat 1. Now you put root n, you're getting this e power lambda square sigma square by 2. So what is so nice about the e power lambda square sigma square by 2? This mgf corresponds to normal 0 sigma squared. Okay, notice this wonderful little property. The centralized Bernoulli, you add it up n times, divide by root n, you get the normal distribution. Okay, that's what happens. As n increases, you're going to get a normal distribution. Okay, so fantastic little result. So the binomial can be close to a normal distribution in some sense. Okay, so this is sort of the root of central limit theorem and how it works. Okay, now you might argue, okay, so this is for the binomial distribution, centralized binomial. Maybe for only the binomial distribution this is true. Turns out that's where the real wonder of the CLT comes. The real speciality of the CLT comes because you can take some other distribution. Okay, so I've picked here one of the other distributions we saw before and looked at the same thing. We repeat the same thing. Okay, nothing has changed here. I've taken n IID samples here. Instead of that simple mx of lambda, now I have a more complicated mx by lambda, which has a certain expected value and has a certain variance phi by 2. Now this is the sigma squared here now. Okay. Oh, here again I've made this mistake here. So it's not minus, it's plus 5 lambda squared by 4. Okay. Apologies for that. Okay. So this is the distribution. It's a different distribution. It's not centralized by Bernoulli anymore. It's some other complicated distribution. But I define the same scaling. Okay, y is x1 plus so on till xn by root n. So now I have to do mx by root n and then raise it to the power n. I get this funky looking formula. So right, some complicated e power lambda by root n sort over and then raise it to the power m. Okay, and here you go. I've plotted this for n equals 1. It looks very out of shape, no, asymmetrical plot which looks a bit different, but as you keep increasing your n, but this time looks like I have to go to a larger and larger n. Okay, so that's okay. N equals 100, n equals 200. It has an asymmetric form, lot of values, but by the time I go to n equals 200, I can start seeing some convergence, right? So you look at the convergence, it's actually converging to once again e power lambda square sigma squared by 2, e power 5 lambda squared by 4, which is again e power lambda squared sigma squared by 2. And from our formula, the formula that we mugged up, right? You remember I asked you to mug up something by heart. This is the MGF of normal 0 sigma squared. Look at that. Look at that amazing little result. So what did we do? We went from n to root n. Okay, instead of dividing by n, we divided by root n, and the distribution in some sense converges to a normal distribution. And it doesn't seem to matter what the initial distribution is. Whatever the initial distribution is, it seems to be converging to normal. Now it turns out this is an astonishing, surprising fact about IID samples. Okay, whatever the distribution is, if you take IID samples, and that's the central limit theorem, the celebrated central limit theorem. Okay, if you take IID samples according to some distribution x, let's say expected value of x is 0. Once again, I told you that's not a serious limitation. You can simply subtract. And variance is sigma squared. And then you do this scaling. Y equals x1 plus xn by root n. It can be any distribution. It doesn't matter. These two conditions have to be satisfied. Then this mgf my of lambda, as you keep increasing n, will tend towards e power lambda squared sigma squared by 2. Okay, and this is the mgf of the normal distribution. This kind of a property is called convergence in distribution. So you say your y converges to the normal distribution in this fashion. Okay, so this is a celebrated theorem. Look at the astonishing fact here. It doesn't matter what the distribution of x is. Okay, you take IID samples, divide by root and add them up and divide by root, and notice that subtle change. If you divide by n, what happens? You remember the previous result I showed. If you divide by n by the weak law of large numbers, the MGF will go to 1. Okay, it converges to 1. But if you divide by root n, you don't go so aggressive on the division. You go by root n. Root n is smaller than n, right? Then it turns out you get a distribution, and the distribution is always normal, and it's always has the correct variance sigma squared. What a wonderful result, right? So it gives you this fantastic thing. This is why the normal distribution is so important in probability and statistics and modeling. It shows up in so many different places, in so many different ways. Okay, this is this central limit theorem. A few observations you can contrast with the weak law of large numbers. If you look at the sample mean, it converges in distribution to expected value of x. And this leads to this general statement. You can make a very loose meta statement saying sum of IID random variables tends to be normal. Do I like it? I don't like it entirely because the scaling aspect is sort of hidden in that, right? The scaling is very important. If you simply scale by 1 by n, it tends to constant, right? So it's not the same as the scaling is not entirely, I mean the scaling is hidden when you say sum of IID random variable tends to be normal, okay? So you have to know in what sense the actual interpretation is. The scaling is very, very important. When you divide by root n, it goes to normal, divide by n, it goes to constant, okay? Interesting little statement about the CLT. The CLT, like I said, is a very, very celebrated result. There's lots of nice experiments. I'll let you read up a little bit on that. So there's this nice, you can build a big experimental setup and draw some marbles from the top or something, and the way it will scatter and it will form a bell curve. So this is why the bell curve shows up quite often in simulation. Statistics are very nice experiments and demonstrations you can do to illustrate how a lot of independent random variables, when you add them up with suitable scaling, you can get a normal distribution to show up. Okay, so this is a wonderful and celebrated result. Okay, so we have not seen the proof of this, and I don't think I can give you a great little proof here. So maybe somebody, okay, so this is again a post on the discourse forum. Somebody can start a post on the proof of the central limit theorem on the discourse forum, and those who are interested can participate. And the proof is strictly out of syllabus. It's not related to your exams or anything. It is just for those of you who are analytically curious about where the proof comes from. Start a post on the discourse forum. I'll also participate. Okay. So how do you use CLT to approximate probability? Now this is important for this course. Okay, so whether you understood the proof for the CLT or not, you should know how the result is to be applied when you want to approximate probability. Okay, so this is very, very crucial. Okay, so you have once again x1 through x, IID x. Okay, IID is missing here. It's IID. Let's say the mean of x is mu, sigma square is variance. I'm defining the sum, y equals x1 plus xn. So notice I'm not worrying about the the scaling and all that. I will use the scaling. I'll show you how to use it in the calculation, but people will usually just write the sum, okay, and you'll see how the probability gets approximated. I'm interested in this question, right? This is the question we asked before when we approximated the binomial. What's the probability that y deviates from the mean mu? Y has n mu as the mean, right? Expected value of y is n mu. Okay. So what is the probability that y minus n mu is greater than delta times n mu? So delta will be some fraction. We'll pick it as 0.6, whatever. So this is the question we've asked before. So how do you use the CLT for the approximation? So it's again IID, I forgot that IID here. Okay. How do you use the approximation? The crucial idea is this y minus n mu divided by root n. When I divide by root n, I'm going to get something that is approximately normal, 0 sigma squared. So in addition, I will divide by a sigma. Okay, why am I dividing by the sigma? So that I get rid of the normal 0 sigma square, and my distribution becomes normal 0, 1. So this is the crucial idea. So y minus n mu divided by root n sigma, I'm expecting it to be approximately normal. So any question you ask me about y, I will convert into an equivalent statement about this normal distribution, y minus n mu by root n sigma. And then find the probability in terms of the normal distribution whose CDF I know. Remember, normal 0, 1, we know it's CDF, right? That CDF is known to us. It's given in tables, it's given in some computer program, whatever. Okay, that CDF is known to us. We can express the answer in terms of the CDF of the normal distribution. This is an approximation. Okay, I've put an approximation there. Nobody knows whether it's an upper bound, lower bound, whatever. It's an approximation, but it works very, very well. Okay, so the CDF of the normal 0, 1 we will assume to be some f of z. This f of z is known to us. Okay, this f of z is known to us. So probability of y minus n mu greater than delta n mu, I'm going to divide both sides by root n sigma. Okay, so I'll get y minus n mu divided by root n sigma is greater than delta root n mu by sigma. Now this I will say is approximately normal, and here I should put an approximation. I'm sorry, I put equal to. This should be an approximation. This is approximately normal 0, 1. Okay. So, probability that a normal 0, 1 random variable is greater than something is 1 minus the CDF of that same thing. Okay. So, this f is known to me and I will approximate. Remember, this is approximate, it is very, very important, it is not equal or anything. So, this is the way in which you use CLT for approximating probability. Okay. So, notice that root n will enter the picture, it is important, and you should know which random variable we are approximating with normal 0, 1. Simple, isn't it? It's very easy to use. I mean, even if you don't understand how all those limits worked out and all that, this is very, very easy to use. Okay, so let me show you a particular illustration. I'm going to approximate the binomial n comma half using the CLT. So mu and sigma are both equal to half, right? Remember binomial. Okay, so I should be careful here. So how do I get this? X1 xn is IID Bernoulli half, and for Bernoulli half these two are true. Mu is sigma as half, right? Bernoulli half is mean is half, variance is 1 by 4, right? P into 1 minus P. So sigma, this is a square root of the variance, is half. Now you remember when we discussed the weak law of large numbers, Chebyshev and all, I was interested in this event, y minus n by 2 greater than 0.6 n by 2, right? So this is the sort of probability I was looking at. Now using the CLT, I keep putting equal to here, I'm sorry for that, it should be approximate. This is approximately 1 minus f of 0.6 root n. Okay, so this f is, this just uses the formula from before, f is the CDF of normal 0, 1. Okay, so that's the formula here, and if I do 10, 50, 100, notice this is same as what we had before. I had the same events listed out. Probability is like 10 power minus 6, 10 power minus 10. Notice the CLT. Okay, it gives you such good approximation, very close to what you expect here in terms of the probability. Okay, so that's the nice thing to know. Approximation is really, really close, and normal approximation is a very, very good thing to do for binomial distribution. So this is how you use the CLT. Once again, not exact, approximate. Not even a bound, you can't maybe prove that, maybe in this case you can prove, but it's a little bit more general than that. Okay. So here's one more example. I've taken our other favorite distribution, y being x1 plus xn, and this x having this distribution. Okay. So here you can again see mu is 0 and sigma squared is 5 by 2, you can do this calculation. Now CLT tells me y by square root of 5n by 2 is roughly normal 0, 1. Okay, so now if I want to find probability that y is greater than delta n, okay, some calculation delta n, I've just done that. Okay, I don't know why I've done delta n, maybe, I mean it's okay, y is greater than delta n seems like a reasonable thing to calculate for this distribution. So it's the same as probability of y by root 5n by delta by 2 greater than, I have to divide both sides by root 5n by 2, right? So if I do that, I get delta times root 2n by 5, and that's approximately now 1 minus f of delta root 2n by 5. Now you can put in calculations. I hope I got this right. Yeah, sure. This should be fine. Okay, so this is the answer. Okay, so that's for that distribution. Now let's do a continuous distribution. Here I have uniform minus 1, 1. Okay. Now for the uniform minus 1, 1 continuous distribution, mu is 0 and sigma square is 1 by 3. Okay. So the CLT tells me root 3 times y, okay, remember y is the summation, is going to be roughly normal 0, 1. So supposing I want to find probability that y is greater than 0.1 root n, y 0.1 root n, just like that, some function, right, so it's okay, some deviation. So multiply both sides by root 3 is the same as p is greater than root 3y, probability that root 3y is greater than 0.1 root 3n, and that's approximately 1 minus f of 0.1 root 3n. So if n equals 100, you know that this probability is roughly 0.2919. N equals 100, this probability is roughly 0.0416. Notice, I mean, I want you to once again appreciate how non-trivial this calculation is. Supposing you want to find the exact value for n equals 100, what do you have to do? Right? You have to find the distribution of y. How will you find the distribution of y? It's the addition of 100 independent, identical, uniform, minus 1, 1 random variables. You have to take the PDF, the individual PDF, and do what is called convolution with itself. So it's a slightly more complicated operation, and find out the actual distribution for 100 and then do an integration from 0.1 root n. Okay, so it's a lot of work. I mean, it's not so easy to do, it's not very pleasing, but notice how easily the normal approximation is giving you the formula. So clean, isn't it? And it's also illustrated in the discrete case. Look at the discrete case. In the discrete case, you have a complicated looking discrete PMF, and if you raise it to the power 100, I mean, you're going to get one big mega expression, and who's going to go in and calculate this probability? It's really hard to do the exact probability. And notice how easy the normal approximation is. I want you to take a step back and appreciate this result for that point of view. Okay, so when you have a sum of IID random variables, the normal approximation is fantastic. It gives you nice expressions. I mean, accuracy is going to be pretty good, and it works out very cleanly. Okay, much better than trying to do exact calculations. Okay, so this is a very popular method in statistics to deal with sums of independent random variables. Okay, so that's the end of this lecture. I hope you understood and appreciated how this CLT comes out of nowhere and simplifies your computations tremendously. Okay, thank you very much. I'll see you in the next lecture.